The next talk is Virt-ICE, the next generation debugger for malware analysis. Please give a warm welcome to NGUYEN Anh Quynh and Kuniyasu Suzaki.
Okay, so in the next talk, we are going to introduce a debugger, which is specially built to analyze malware, and the debugger is named Virt-ICE. So we had two people here, and we are from a national research lab named AIST from Japan, and my name is NGUYEN Anh Quynh. I'm a researcher in AIST, and I'm also a member of VM security team. Here's Mr. Kuniyasu Suzaki, who's a senior researcher of my team. And in my team, we have multiple interests. We have interest in operating system, virtualization, trusted computing, malware analysis, forensic, rootkit, and intrusion detection system. Okay, so about research area related to the virtual machine, we did some research. We focus on protecting virtual machine. First of all, we do research to perform live memory forensic for virtual machine, or we develop malware scanner for virtual machine. And we also use virtual machine for many research topics like dynamic binary analysis or vulnerability research. Okay, so here's a preview of Virt-ICE. Virt-ICE is a new debugger which is specially built to analyze malware. So the reason we need a new debugger because on the current debugger has many problems which cannot be fixed. And to build the Virt-ICE, we have a new approach, and we fix most problems of the current debuggers. And our debugger provides many functionalities targeting malware analysis. So you can use Virt-ICE, and we hope that your job will be easier. Okay, so in this talk, we first introduce the problems of the current debuggers when we use the current debugger to analyze malware. After that, we introduce the Virt-ICE solution. We focus on the architecture, design, and implementation of Virt-ICE, and we present the main features of Virt-ICE. After that, we have some live demo so we can see how Virt-ICE really works. And next, we have some discussion. So we discuss the limitation of Virt-ICE, or the future plan of this project, and finally, conclusion. So in the first part, we introduce the problem of the current debuggers when you analyze the malware with those debuggers.
Okay, from here, I'll talk about the method of malware analysis. So for malware analysis, there is two methods, static analysis and dynamic analysis. In the context of static analysis, in the context of malware analysis, static analysis disassemble or decompile malware binaries. So static analysis analyze the decompiled, deassembled malware code. So the code is used to understand its activities. Unfortunately, current malware are packed and obfuscated. So the analysts have to understand packed and obfuscated. So it is difficult. So to avoid the difficulty, we use dynamic analysis. Dynamic analysis run malware and monitor its activities. So running malware unpacked and de-obfuscated by itself. So it is easy to understand. For dynamic analysis, we use debugger. So we can run malware under the monitor of a debugger. The debugger has many functions. So debugger disassemble or decompile malware binaries. And we can monitor the execution flow using software or hardware breakpoints. We can also monitor the data flow using memory watch point. If we want, we can run the malware with single-step mode, etc., etc., etc. We can get very useful functions. However, debugger has a malware in the context of malware analysis, because malware can detect the debugger and change the behavior. So malware is being debugged or monitored and change the behavior differently. For example, to stop the execution or to act as a normally. So then Chen reports the popularity of anti-debugger technique in NDSS 08 paper. He said 93.9 malware have anti-debugger techniques. So it means most malware has an anti-debugger technique. And another problem is malware can tamper with debugger, because debugger has also vulnerability. So malware can attack the debugger. So from here, I'll talk about the detail of detecting method and attacking method. The first technique is use system service, because debugger use system service to handle debug event. Malware can detect the service. For example, Windows OS leaves trace in a various place about the existence of debugger. Windows OS, the process on the Windows OS has a PEB. PEB means a process environment block. The PEB has two flags, entity global flag and being debugged flag. So this flag means the process is debugged or monitored. So and Windows offer us some API to check the flags. So malware can use this API to check the to check malware is debugged. So here is a list of Windows 32 APIs. Second technique is to identify the integrity of malware codes, because debugger modify malware code, malware binary code to set breakpoint. So debugger insert CC instruction instruction in the process of memory. So this figure shows method. Debugger inserts the breakpoint. The breakpoint can check the malware. Malware can perform self-checking to detect the debugger. The third technique is to check the particular system resource, because debugger uses system special system resource in the same system. For example, debugger has its own file name when it is installed, and malware can detect the file name. Malware can also it is debugged, because running debugger uses a special process or a special window name or special kernel devices. So malware can detect the debugger. Malware also tamper with debugger. So malware can change the debugger behavior differently. One technique is malware can modify hardware breakpoint to change the behavior of debugger. Malware also resets the software breakpoint to original value, so the debugger is not triggered anymore. Malware also can attack the debugger. For example, malware issues function called terminated process to stop the debugger. This technique is used to detect and attack the debugger. So from here, Quynh will show the demo.
Okay, so here I show you one demo. I don't use a real malware, but I use one CrackMe. CrackMe is kind of program that is used by people who want to exercise the reversing skill. And this CrackMe, to make it harder for you to reverse it, it uses many anti-debugging techniques. Yeah, this CrackMe. So your job is that you need to type the right key to here. And click try. If you type the wrong key, you can see that you haven't bought the program. So your job is that you have to find the right key by reversing the binary. And this CrackMe has many anti-debugging techniques. So first of all, I can now run the CrackMe and I run the only debugger here. Can you see that? I cannot run only debugger because this CrackMe detects the debugger and shut it down before it even shows up on the screen. So to make it more clearly, I run the debugger and I open the CrackMe. Okay. Now I will run this CrackMe inside only debugger to see what happens. Okay, run. Can you see that? It shut down the debugger because it detected it's being debugged by your only debugger. So this CrackMe has many anti-debugging techniques and it can detect debugger and after that it attacks the debugger, shut it down. So coming back to our slide. So you can see that detecting debugger is very easy. And unfortunately, it's increasingly complicated techniques are introduced. First of all, Peter Ferry from Microsoft, he published 9 series of papers about anti-unpacker tricks that include many anti-debugging techniques. And I think he's going to publish more and more tricks like that in the future. So attack and tamper with debugger is also very trivial. But unfortunately, all those problems cannot be fixed. You can have plugin for debugger to work around the problem. You can manually nullify the anti-debugging technique in the binary of the malware, but that doesn't fix the root of the problem. And it also takes a lot of time and skill. So the question is, why you have all of these problems? Any idea? Why? Why you have so many problems when using debugger to analyze malware? Okay, the answer is very simple. Because the debugger is never designed to analyze malware in the first place. because the debugger is built by developers to debug the legitimate software, to find the software bugs. And of course, the developers never write software to defeat his debugger. So I think that people just happen to use the debugger to analyze malware because they know how debugger works, and the debugger can be used to change the execution of the malware. But the debugger is never built to analyze the malware, and that's why you have so many problems, and all of them cannot be fixed. Okay, on the second part, we introduce the Virt-ICE problem, the architecture, design, implementation, and the main features. So here's our idea to solve all of those problems. So because the malware can detect the debugger, so we try to solve that by making the debugger invisible to the malware. So malware cannot see the debugger anymore. So we solve that. Second one, because the malware can detect, can attack the debugger, so we try to put the debugger out of the reach of the malware by running the debugger in another protection domain, so malware cannot attack it anymore. So we solve two problems. And here's our approach for Virt-ICE. We run the malware inside virtual machine. And this requirement actually doesn't introduce any problem because already people already use virtual machine to analyze malware for a long time. So this one is not the burden for malware analysts. And running inside malware inside virtual machine, we use fine-grained instrumentation technique. We instrument guess virtual machine to intercept guess execution at any time and at anywhere we want to. And after that, we put the debugger specifically inside the hypervisor or emulator layer of the virtual machine. And the debugger staying here, so it is out of the reach of the malware running inside the cache. The cache cannot attack the debugger running at the lower layer. So here's the architecture. So you can see that we run the malware inside the cache virtual cache VM, and we run the core component of the Virt-ICE in the hypervisor layer. So there's some other benefits for Virt-ICE. Because we run the debugger inside the hypervisor layer, so we have the whole system view, so whole system analysis is possible. And especially ring zero code, for example, rootkit, debugging is better than anything else available out there because you can debug anywhere, anytime. Normal debugger can also be used to debug the kernel, but there's some restriction. For example, there's some place you cannot debug, and there's some restriction that you cannot overcome. So this approach helps us to fix all the unfixable problems we introduced before. So you can see that Virt-ICE is invisible to the malware. Why? Because normal debugger uses system service for debugging, right? But Virt-ICE doesn't use a system service because we use instrumentation from the bottom layer, and we can even have better technique to debugging. The second problem, the normal debugger modifies malware process. Virt-ICE doesn't do anything like that because instrumentation at the bottom layer never modifies the malware process. We don't need to modify malware process. We don't need to inject software breakpoint into malware process. And finally, the normal debugger is staying in the same domain with the malware, but Virt-ICE stays outside in the lower layer. And we never use any agent inside the cache. We don't need any help from the cache. We need zero help. So we stay completely outside. So we are completely invisible. And finally, Virt-ICE cannot be attacked by malware because it stays at the lower layer. And malware cannot attack to the outside. That's guaranteed by the virtual machine design. Okay, so here are some requirements to build when you build Virt-ICE. First, you need to understand the cache context from outside. You run debugger outside, but you need to understand the cache context from outside. without any support from the OS inside. And after that, you need to instrument the guest virtual machine execution. So using the instrumentation, you can set breakpoint, watchpoint any way you want to. And after that, from outside, you need to access to the virtual machine context. You need to read and write to virtual machine memory. You need to read and write to CPU context of the guest. And finally, Virt-ICE also need to manage the virtual machine. You need to pause virtual machine, resume virtual machine when you want to. And those are all the requirements you need to satisfy when you build Virt-ICE. Okay, so on the first problem, how to understand guest context from outside. So know that we must do everything from outside without any support of the guest virtual machine. And this is called virtual machine introspection problem. And on this part, we use the work done from last year. So we can see our presentation at several conferences last year. And we use a framework named NGUYEN. NGUYEN framework help us to extract the OS semantics object from the memory of the virtual machine. And now we support Windows OS. Okay, so on the NGUYEN need to access to the guest memory and CPU context from the host, from the lower layer. And to access to the guest memory and CPU context, we need the help from the Kubota framework, which we introduce later. After that, after we can get access to the memory and CPU context, we need to get the OS objects from the memory of the guest virtual machine. And because we are focused on malware, so we focus on getting the object that can be exploited by malware, like network port, connection processes, DNN, registry, kernel module, and so on. Here's a full architecture of NGUYEN framework. You can see that NGUYEN framework is split in multiple layers. And each layer, the bottom layer, provides a service to the higher layer. So to build NGUYEN, you have many challenges. There are two challenges. There are just one challenge. NGUYEN need to get a semantic object from the memory of the guest virtual machine. And this job requires excellent understanding on the OS internals. So to get OS object from the memory, we have two things to do. First, we need to locate the OS object. We need to, first of all, you want to get all the processes running inside the guest from the memory. You need to locate all the process in the memory. And so on, if you want to get a list of all the kernel module in the memory, you need to access to those objects of the kernel module, and so on. So on this part, actually, we don't invent anything new. How to locate those objects already presented by many research in the community. You can search many people on how to locate those objects in the memory. Okay, so after you locate those objects, you need to get information from inside each object. First of all, you can locate each process object somewhere in the memory. But that's not enough. After that, you need to extract the malware field from this structure in the memory. So first of all, if you want to know the create time of this process, you need to know that the create time field of this structure stays at the offset 70. And this field has a size 8. Right? You need to know where it stays in the structure, in the size of that. And so that means you must understand the object structure. But the problem is that those structure, the format of those structure can be changed between Windows version and even between service pack. It's not fixed. First of all, Microsoft can insert a new field in the next version of Windows anywhere or they can exchange those field, those two field anytime. So the offset is not fixed, and sometimes the size of those fields are not fixed either. So how to solve this problem? So there are many work also want to extract the object from the memory like that, and the solution is that they hard code on the popular objects and offset and size of popular field in the program. Everybody does that, but that's not good enough for us, because this solution you can only extract information, extract limited information, just limited to the object you specify your source code. It's limited to the offset you specify, and for those not specified, you cannot extract out. So I have a dream. I want to be able to query structure of all the object in Windows OS with all the field inside each object, and I want to do that with all the OS, not only Windows. And I want to do that on demand at runtime, not at compile time, with all kind of objects. And I want to answer many questions. First of all, I want to know the size of these objects. I want to know the offset of this member field inside this object. And we solve this problem with one framework named Virt-ICE. And Virt-ICE satisfies all the requests and make your dream come true. It's another framework. And Virt-ICE rely on the public information on OS object. It doesn't depend on OS actually. And this framework supports Linux and Windows now. And we extract information by relying on debugging format. And we extract them from the debugging format. So for Windows, we have no contact with Microsoft, so we need to rely on the public information. And one of them is React OS. React OS is open source OS, which try to emulate Windows. So the idea is that you can run Windows software without needing to buy Windows OS. So you can run Windows software on React OS. And React OS is free and open source. Support from Windows 2003 and up. Windows XP and prior version are not supported. So here's simple React OS code. Of course, this one is only patched by me because the original React OS information they don't support Windows XP. So you can see that the structure is defined based on the Windows version. If Windows is before Windows 2003, it has that field. If Windows is after Windows Vista, it has those fields. So we build the Windows object. We compile React OS file header to prototype with debugging information. And after that, we extract information from the debugging file format. So first of all, here's how I build the object for Windows XP. We use Z++, build a dummy file which only include some object file I'm interested to, and I define the Windows XP macro, and after that I output one object file for Windows XP. And the object file Windows XP service factory.o include all the information about all the object file, about all the structure of Windows. So there are some problems. Anyway, React OS only support Windows 2003 and up, as I said. So I need to patch React OS header to support Windows XP. And I rely on the information from Windows debugging simulator, and patch size quite small. I also need to fix React OS prototype to support other Windows OS like Windows Vista or Windows 7. So here's a simple API for Virt-ICE. You can see that there are three functions. You can get the structure side is a top function. Just give the structure name. Second function give you the member size of the member inside structure. Just give it the structure name and structure member name. The last function give you the offset of that member, give it the same information, structure name and the struct member. So here's the simple code. You can see that for Windows XP, you can decide that at runtime, not at compile time. You open the Windows XP object file. After that, you call di structure side to get the side e-process structure. The next line, you get the size of the create time inside e-process. And the next line, you get the offset of create time inside e-process. And after that, when you are done, you close the API. So everything can be get from the object file, and it's very flexible and decided at runtime, not at compile time. Okay, so you and I can access to the memory, can understand very well the structure of every object in the memory, so you can get all the information you want to. Here's some simple API. You can see that the first function, you can use that to get the first process in the list of all the processes in the memory. You get the next process using the next function. And you repeat calling get task next until you get the last process in the list of all the processes in the memory. You can get the process ID, DNN file, all the DNN file opened by that process. Yeah, there are a lot of functions in NGUYEN, and it can give you all information you want to. It's very easy, just know how to use it. So here's the architecture. Finally, the bottom layer gives you the information about all the structure. And you have the object file is the bottom, and the top layer extract all the object from the memory for you. Okay, so we solve the first problem, how to understand the guest context from outside. You can get everything from outside. You can see everything from outside. That's like we stay inside. So the next problem is that we base Virt-ICE on virtual machine. So we need to choose virtual machine for Virt-ICE. Which virtual machine to choose? So because we need to customize virtual machine to instrument it, so of course we need open source virtual machine. Therefore, software like VMware is not suitable. So there are few choices. NGUYEN it's not good. Because why? Those virtual machines run most instruction directly on the CPU. And if you want to instrument at every instruction, you need to run the CPU in single step mode, or you need some very weird trick to intercept at every instruction. And that makes the virtual machine very slow. So NGUYEN is not good because it's too slow. However, VirtualBox another open source virtual machine, but it's like NGUYEN. It runs most instruction directly on the CPU. So we reject this option as well. The third one, Box. Box is one open source emulator which translates all the instruction and execute it right after it translated. So Box is quite good because Box translates all the instructions, so we can mess up with the translation process and you can instrument the virtual machine. But there are some problems. Box is very slow. It's quite slow. And another problem is that Box doesn't support some Windows OS very well. For example, I had some problem when running Box with Windows Vista or Windows 7. So Box is not good for me either. So the last one, it's a good one, QEMU. QEMU is one open source virtual machine released under GPN license. And it also translates all the instruction by software. But it has some trick to improve the performance. So QEMU is quite fast compared to Box, much faster actually. And it's quite usable actually. So we choose QEMU. And we we designed Virt-ICE based on the latest version of QEMU at that time, which is 0.12.4 version. The latest version is 0.12.5, which was released last week. Okay, so here's architecture. Virt-ICE consists of two components. The core component runs inside the emulator layer of QEMU, and Virt-ICE module runs inside QEMU process below the guest virtual machine. And Virt-ICE is built on top of two frameworks. One is NGUYEN framework, which I introduced before, and the second one is the Kubota framework. This framework is to instrument the virtual machine. We have the front end named Virt-ICE client to connect to the Virt-ICE module to send requests and get back the answer, and show it for people to see. Okay, so how about instrumenting guest virtual machine? We need a framework named Kubota, and this is the generic instrumentation framework, because we want to build a framework that is generic, so that can be used for all type project. And actually, we build Kubota not only for Virt-ICE, but for some other internal project in my team. And Kubota instrument virtual machine by instrumenting the binary translation process. Kubota does that by put the hook at the right place inside the binary translation process, and those hooks will go now to external instrumentation handler. And Kubota framework also support dynamic loaded module built on top of Kubota framework. And those modules built on top of Kubota will provide the external handler, which will be executed when we hit the Kubota hook in the instrumentation layer. So when building the instrumentation framework Kubota, we have many challenges. First one, originally QEMU doesn't provide any support for instrumentation, so we are on our own. We had to build Kubota framework from scratch. And the second problem, it's not like Box is very easy to understand, which translate every instruction after that, run it immediately. But QEMU, inside, it has one just-in-time compiler engine. And it uses this compiler to perform binary translation. And this compiler, just-in-time compiler, makes the binary translation process very complicated, and it's hard to understand. So at first, the compiler needs to translate code from the cache, and the translate code is safe, and those code will not be translated again if it's available in the cache. So the cache can be reused to improve the performance. So for this reason, we need to dig very deeply inside the translation process of the just-in-time compiler to provide the instrumental hook of Kubota. Okay, so we can talk a bit about how the just-in-time compiler works. So just-in-time compiler translates guest code to TCC intermediate representative, and after that, it translates the TCC language to native code, which will be executed on the host. And the translated code is cached to be reused, so the performance is much better than emulator like Box. And the translation is done on the code block basic. So QEMU has the compiler has some tricks to improve the performance even more. For example, the full CPU context, which include register, segment register, control register, and so on. The full CPU context is only saved at the end of each block. So that means the CPU context is only guaranteed to be synchronized at the beginning of each block. So as a middle of the block, the CPU context is not synchronized. It's out of sync. But the problem is that if we put the instrumentation hook in the middle of the block, you cannot get the fully updated CPU context. So in our computer framework, we need to synchronize CPU context ourselves when needed. And unfortunately, on Intel platform, QEMU only have E flag as out of sync context. So we only need to synchronize the E flag value. Everything else is always synchronized. Okay, so to build the hook, we instrument at the TCZ level. After the target code is already translated to the TCZ language, and this is required because the translated code is cached, and it's not translated again if it's already in the cache. And when we build the instrumentation hook, we avoid putting the hook into the architecture-related code, so you can support all the architecture universally in the same way. But there are some exceptions. For example, you want to instrument at the instruction level, you need to mess up with the architecture code. Or if you want to instrument at some architecture-specific places, like you want to instrument when the control register are updated, or when instruction like read and write to a modern specific register is executed. You need to mess up with the architecture code. And sys enter says it true. And finally, we need to make sure that the performance overhead of computer is minimized when no instrumentation hook is registered. Here's one simple example on how I instrument the sys enter instruction. So we put instrumentation code deeply inside the TCZ generated code. And you can see that we check if is there anybody register sys enter event. If no, we skip. So you can see that if nobody register the sys enter hook, there's almost no performance overhead. And after that, because you don't always need to have the fully updated CPU context, you are not always interested in E flag register. So only in case you are interested, we synchronize the CPU context. And after that, we call on the register handler for sys enter. Yeah, so this framework hook virtual machine at many places, which we think that is useful for generic purpose, not only for this project, not only for Virt-ICE, but for everybody else. So you can see that we currently instrument at many places. So you can have fine-grained instrumentation. You can instrument at begin and end of each instruction or each block. You can instrument when the jump or call instruction is executed. So we know when the target is reached. You can instrument when the interrupt begin or finish. We instrument when the sys enter, sys exit, sys call, sys reset instruction are executed. So you know when the sys call operating system call is executed. You can instrument input and output to the physical port. You can know when the control register are updated, value are changed. You can instrument when the code read or write to the modern specific registers. And finally, it's very important. You know when the memory access event, read or write to the memory anywhere in the virtual machine. You can instrument that and you can get your code notified. Yeah, so another challenge when building computer. The original QEMU is very slow. And people can accelerate the QEMU process with KQEMU. KQEMU is a software-based solution to run most instructions directly on the CPU. So QEMU, together KQEMU is much faster for you. So it's good to use QEMU. And we use QEMU with computer, so we dynamically, because KQEMU run most instructions directly on the CPU, but when we instrument the virtual machine, we don't need that. So we turn on KQEMU only when nobody registers with the instrumentation framework, and we turn it off when instrumentation is required. But unfortunately, KQEMU support is dropped from the QEMU version 0.12.0. That means you only have support for KQEMU from 0.11 dot something and before that, but not from 0.12 version. So we had to forward port KQEMU to 0.12.4, which is the version we build Virt-ICE. Yeah, so now we have the instrumentation framework layer. What to do with that? Of course, we build our code on top of that framework, and we call that a computer module. Computer module is built to register with the computer framework at the lower layer for interested instrumentation events. And computer module provides the instrumentation handler for those events. And those handlers will be executed when the event happens inside the guest. And our module also need to access the virtual machine. So we need to do something like we need, from the computer module, we need to pause or resume virtual machine on demand. We need to read and write to virtual machine memory. We need to access to CPU context of virtual machine. And also we need to dynamically enable or disable instrumentation hook. So how to do that? We build computer module as just as normal dynamic link module, dynamic link code. First of all, in Linux, that's .so file, share object file, or .enn on Windows. And you can load the module into the QEMU process because operating system provides some service for us to load the DNN file inside a process. And you can see that using this approach, it's very easy for you to implement the computer module because it's just a normal DN module that you are very familiar with. Okay, so now we have module. You need to manage that, right? So we extend QEMU with a new command, K-module, to manage the computer module. And we need to support unlimited number of computer module to be loaded at the same time. Multiple module can run at the same time on top of the framework layer. And we can also reload the module with the different parameters. Now, we need to load the computer module inside the QEMU process. That's very simple because we just simply use the DNN service provided by the OS. First of all, on Linux, we use DN open function to load the share object file into the QEMU process. And we support load the module in string parameters, so you can specify the option to run the module. And finally, you need to unload the module when you don't need it anymore. And we also use another DNN service provided by the host OS, which is DN close on Linux. But there's one problem. When you want to unload the module, if you call DN close, the module will be immediately unloaded from the memory. So what happens if the instrumentation handler is still running at that time? The whole virtual machine will be crashed. So unloading the module from the QEMU process is not simple. It's not trivial. So we have some technique to make sure that you can safely unload the computer module from the memory. we use a reference counter for each Kubota instrumentation handler. And we associate each handler with a reference counter internally. And we increase the counter before running handler and decrease it after the handler is done. And we only run the handler when the module is in enable state. Now, when you want to unload the module from the memory, first we put the module in the disable state, and we signal the module to interrupt itself. And we have one dedicated manager thread to periodically check for the reference counter of the module to be unloaded. And we only unload the module when the reference counter reach 0 value. So after that, it's safe. So actually, this type of a synchronized mechanism to unload the module. We might not unload it immediately, but it might take some time. Yes, so now our module need to access to the guest virtual machine, as I told you before. We need to pause or resume the guest. We need to access to the memory or CPU context. We need to register the hook with the Kubota framework layer. But all those functions stay deeply inside the QEMU and Kubota layer. And we need to export all of them out for the external Kubota module to use them. So how to export those functions? There are two ways. Two ways to export those functions for the external module to use. So first way, we can refactor the QEMU code to export the required function out for an external DNN library. So the same library can be linked to both QEMU and Kubota module. So Kubota module can access to the function using by QEMU too. So from the engineering point of view, this one is very nice, but it's also very complicated because too much code need to be refactored, and there are so many code for each architecture which mess up, and if you want to if you want to refactor all of them, it take a lot of time, and you change the code a lot, and we don't like that. The second way is that we just selectively export the needed function pointers out for Kubota module, and after that we transfer the function pointer to Kubota module when we load it into the memory. And this way, it's extremely easy to implement. You need very small patch and require minimum modification to QEMU. So we go with the second way. Here's how we export some function to the Kubota module. We put all the function we need to export to one structure. So you can see that we put all those functions in the structure and keep the rest of this structure to the Kubota module. So the Kubota module can read CPU context, write CPU context, read and write to the physical memory. It can know the memory size of the virtual machine. It can know how to translate the virtual arrest to physical arrest. It can pause or resume virtual machine. It can manage the instrumentation hooks. Here's how the manager function is organized. You can see that at the bottom. The manager function is just a function pointer that takes 3 values. You need to know that you want to install or delete the instrumentation hook. You want to know that you need to register which type event: jump call event, instruction begin, instruction end, sys enter, memory read, memory write, and so on. And you also decide if you want to synchronize the CPU context or not. And at the bottom, you don't see that just one function pointer. So we register the function pointer which those instrumentation hook with those conditions you can give to the function handler, to the manager function. So here one simple code for Kubota module. Kubota module have some fixed requirement. You need to provide two functions, to init and initialize and exit. Initialize is executed when the module is loaded, and the exit function is executed when you unload the module. So first of all, in this screen, you can see that I register one function, one instrumentation handler to be executed when sys enter happen. And I don't care about CPU synchronize. I don't need to synchronize that to improve the performance. Yeah, so remember that Virt-ICE consists of two components. The core module stay inside the emulator layer, and the client stay outside. So the server is only a computer module. And for now, you register some instrumentation hook on demand, not anytime, only when we need. Jump call, begin and end of instruction, begin and end of interrupts, so we can intercept the syscall using the interrupt tree in our version of Windows. Sys enters and sys exit to intercept system call, memory access event, so we know when the go read and write to the memory. And we also use the NGUYEN framework I introduced before to access to object in the guest memory. So here's the architecture again. Our module is built on top of two frameworks to instrument anywhere you want, and our module can also access to the anything inside the memory. You understand everything inside the memory, on the context of the OS. Yeah, what's up now? And the client send the request to the module and get back the result. The client is very simple front end. It doesn't do anything special. So to handle the request for the module, we have a separate thread to handle the external command sending from the Virt-ICE client. And we use TCP protocol. And through the TCP, we receive command from client, which can be used generic command or debugging command or the command to monitor the virtual machine. And Virt-ICE also using the exported function from the computer to manage the virtual machine. Read and write to memory, CPU context, run single step mode, or enable, disable instrumentation on demand. Virt-ICE currently provides some generic commands. So from outside, you can inspect the guest virtual machine. So there's some thing you can do. You can see the process, you can view the memory, you can see the PE file in the memory, you can read and write to memory, you can search in the memory. You can see the process, you can see the own DDN file opened by process, you can see on the kernel module, and so on. So here's a simple demo. So here on QEMU, I run Windows XP Service Factory. And QEMU has one monitor interface for you to control the QEMU. So you just type the command on this interface. So now let's see if there's any computer module is loaded. I run the computer module command, which is we build this command by extending the QEMU. So we say that there's no computer module enabled loaded inside the QEMU. People stay out at the end. Can you see that? But I cannot make it bigger because this is fixed with QEMU. I cannot make it bigger, sorry. So, inside that there's no computer module loaded. Now, I will load the Virt-ICE module inside the QEMU. So, Virt-ICE module is built and put on somewhere on my hard disk at this place. So now I will load this module into QEMU. Okay, module load, and we specify the where we keep the module. Yeah, so it's loaded inside the QEMU. Now we can check again. Run the K module command again. And inside that, there's one module loaded, named Virt-ICE inside QEMU. So that means you already loaded the core module inside the QEMU. Now we use the Virt-ICE client connect to that module. So I have another window here. You can see that, right? Now I run Virt-ICE. Yeah, Virt-ICE Skype console interface, and you can type command here. For example, Virt-ICE have command name PS, so you can see all the process running inside the guest virtual machine. You see that? You can see all the processes. That include the process ID, parent process ID, the created time, the path. Now, for example, I run Notepad. This again. You can see here, Notepad is here. The latest process, the new process. And I can also list all the process in the tree. So you can know that Notepad is a child process of Explorer.exe. Now, if I close Notepad, this again, Notepad is gone, right? It's gone. Not only you can do many things. For example, you can see all the kernel module loaded inside the guest. You can see the system code. You can pipe that out, so you can use less to pipe that out to monitor that, to inspect that. You can see the IDT table. You can see ZDT table. There are a lot of things to do. And you can come back to Notepad. You can see, for example, DNN file opened by Notepad. Notepad has process ID 788, right? DNN -P 788. Yeah, they are all the DNN file opened by Notepad. Now, if you can see even more, for example, you can see which function is exported by kernel 3032.dnn. How to do that? Have another command name PE, specify process ID here, specify the header of the DNN file, and export function. Okay? What? Okay, -H, sorry. Yeah, they're on the exported function by kernel 32.dnn. So that means you can know a lot of things inside the guest. Yeah, I know. Don't worry. Now, from outside you can see everything, know everything just from outside, without any support from inside. Debug command, Virt-ICE. Virt-ICE supports some normal command to debug. So you can debug malware. You can set the execution breakpoint. You can set memory watch point. You can do single step. You can do step over. You can run until red, return. You can disassemble. You can pause virtual machine. You can resume virtual machine. Now, for example, I run the crack me. Okay. Now crack me run normally. There's nothing wrong because there's no debugger running inside the guest, so it runs normal. Now let's see. Type something here. Click, and Windows open. That means you type the wrong thing. So now I want to put the breakpoint when this window is open. Okay? So you can see how Virt-ICE works. So we have db command, process. This one is debugger, right? You can specify the process ID by using the name too. And we specify the function we want to set the breakpoint, which is message box. Okay? So you can watch this, the behind window is running. Okay? Now we put the breakpoint. You can see that the virtual machine is paused. So we can input more breakpoint we want to. Now I can list all the breakpoint set by the last command. So you can see that when I set the breakpoint on message box, Virt-ICE is smart enough to set two breakpoint, what two version of message box. One is for Unicode version, one is for ASCII version. Okay, so after that you can resume the virtual machine. So let it run. Okay, so when you resume the virtual machine come back to running state normal. Now click try. Can you see that? Virtual machine become stop because that function is hit. So coming back to the debugger, you can see that. You can see function message box A is executed, and this message box A will show the text you haven't bought the program yet with the caption NAG, NAG, right? That's what we expected. So you can do a lot of things now. For example, you can disassemble the process. Process ID is 1260, right? And where you want to disassemble, for example, this function specifies the address, how many instructions, 20, for example. And here, you can disable the guest code, so the binary and the malware code from the debugger. Okay, so after that, we resume the virtual machine. db-r. Okay, it's running now. And it's open. The message box, which is we expected, right? That text and that Windows caption. Okay, now you can let the malware continue to run. But from the debugger client, you can stop virtual machine anytime to input the new breakpoint or to inspect the virtual machine by Ctrl+C. Okay, Ctrl+C, and the virtual machine becomes stop. Now you can, for example, list the breakpoint and remove all of them. Minus that. Okay, we remove all the breakpoint. Now we run this one again. Okay, now you click here. Nothing happened. It's not stopped because we remove all the breakpoint. So the debugger is not triggered anymore. Next one, there are a lot things to show. I show you. I have 5 more minutes, that's enough. You can set the breakpoint, set watch point memory, single step, and so on. And there's some advanced feature Virt-ICE. Virt-ICE is not only a debugger, but it includes some more advanced feature to make the job of the malware analyst easier and more fun. First of all, we include some function to monitor the malware. For example, if you want to monitor all the function related to the file by this currently, we have another command, db-process debugger, and we specify all the function we want to know about. And we put all the function in one file and specify here. All the function name, all the API name specify here. And the good thing is that monitoring means you see the output, you see the information, you see the function executed by the malware, but we don't stop the malware, but still let it run. Okay? Now, let it run. Okay, and let me execute this one again. You see at the bottom window, this correct me run a lot of function, and Virt-ICE is smart enough to tell you function name, parameters of each function. So we can monitor the behavior by monitoring the API executed by the malware. Okay, more than that, we have something else to show. Okay, so our debugger is can find all the anti-debugging technique. So the malware doesn't know that it's being debugged from outside. But more than that, we can also report on the anti-debugging techniques used by the malware. So we know which debugging technique is used by the malware. So here, the last demo. You want to see all the anti-debugging technique used by the malware by run this command -a. What? Okay. Every anti-debugging techniques and resume. You see that? This correct me continuously execute the is debugger present, which means anytime if you attach the debugger into this correct me, it knows that and it will shut down your debugger. So by this function, we know that which anti-debugging techniques this malware use. So there's a loop. This correct me must have a loop and continuously check the debugger to see if the debugger is coming. Okay? You can also, the last one, you can also monitor not only the API but also the system code. Monitor all the system code, okay? What? Yeah, this can be execute a lot of system code. Okay, so you can see that how the Virt-ICE is designed, how the Virt-ICE really work. Conclusion, I skip some slide, not very important. Virt-ICE is a new debugger that can fix most problems of current debuggers against malware. We use a virtual machine technique. Virt-ICE is invisible against malware. It cannot be attacked by the malware, and it provides rich functionality for malware analysis. And we plan also to provide a lot more function in the future. Not only those you saw. So any question? Only 30 seconds. Yes. Not yet. Yeah, we put it to the public, but currently the code is very messy. The computer framework changes all the time because we consider many things to improve the performance. So we haven't done any benchmark yet, and there are a lot of things to do before you can put it out to the public. But we want to put it to the public for people to use, and some component of this project will be open source under GPN license. Yes. Timeline attack? Timeline? No, not yet. Okay, we can talk outside. Yes. Okay, good question. Okay, last question. Okay, we have one slide about anti-Virt-ICE. And there are many malware that has anti-virtual machine technique, right? But you can see that there are two problems. One is anti-debugging and anti-virtual machine, right? So some malware has anti-debugging, some malware has anti-virtual machine, and some malware has both. So we fix this problem, but we don't do anything with anti-virtual machine. And this is our scope of this research. And you can say that everybody suffer now because everybody use debugger in virtual machine. We don't use a real physical machine to debug malware, right? So everybody suffer, not only Virt-ICE. But we fix the anti-debugging problems. Sorry? Yeah? CC instruction? Now we instrument the malware, so we never write anything. No, I think there's some mistake. I think maybe he misunderstand something. We can talk outside. Yeah. Okay. Okay. Okay, thank you. You can talk outside, and in case you want to contact, you can send to our email.